Hello everyone, today let's solve the problem 190 reverse bits, right? So what the question states here, we have to reverse the bits of a 32-bit integer, and what we need to return, we have to return the resulting integer basically, right? So input is a 32-bit signed int, right? So input is a this one n equals something they have given, right? So this is a 32-bit signed integer, so we have to treat its bits as unsigned when reversing. When reversing, we have to treat its bits as unsigned, right, as unsigned basically. So let's do one thing. This is it for the question basically. This is the easy basically this is easy based question, see here, and this is it for the question. Just give me a second here, let me change the color. 1 second, just give me a second. Yep. Now we will be making use of the bit manipulation to solve this problem, right? So we will be making use of bit manipulation to solve this problem. Just remember this, right? So we don't have to go with the string or the array, this one string or the array conversions. We can just go with the bit manipulations. It will be easy for us, right, to solve the problem if we make use of the bit manipulation. Let me delete this one. Yep. let me consider, let's go with the example one, right? So let's do one thing. Let's directly this one discuss the approach by considering the example one. It is same for the example 2 as well, or let's do one thing. We can just check this one, example 1 and example 2. See here, the example, this is 32-bit signed integer, and the output that we got here is this one. The same thing goes with the example 2 as well, 32-bit signed integer, and 32-bit this one. The output that we got here is this one. This is fine. So yeah, you can just look into the constraints as well. They have given here n less than or equal to this one, n greater than or equal to 0, and less than or equal to 2 to the power of 31 minus 2, and they have said that n is even, right? So just keep that in mind as well. This is fine, man. Let's consider example 1. They have given wonderful examples, right? Just for the sake of understanding here, let's consider example 1. So here example 1, n we have been given 4 3 2 6 1 5 9 6, right? So n this one binary, so here they have already given this one in n in the binary for this one 32-bit signed integer. In the binary, this one 000 ending at 1000 basically, this one, right? So this is fine. And after reversing this one in the binary, we get this one. When we consider this one binary in the form of digits, so this one will be 964176192, right? So they have already mentioned this one, right? So let's see the approach. First we'll be maintaining the resulting variable, right? So we will repeat this one 32 times, right? So let's discuss the algorithm or the approach. First we'll be maintaining the resulting variable to store the result. Initially we'll set the result to 0, right? So we'll set the result to 0, right? So what we will do, we will take the least significant bit of n, right? So we'll take the least significant bit of n. So here, let me write it from here. So result equals 0 initially. We have to store the result somewhere. So we are going with the resulting variable res here. Next step, we'll be taking the least significant bit of n. Here n followed by this one bit equals, so this one will be n bitwise and 1, right? N bitwise and 1. So what we will do here, we will append this one, append it to the resulting variable res as the new least significant bit after shifting result left, right? After shifting the result left. So we can just write it on this way, result equals result. So we'll be making use of the left shift operator as we had discussed. So this one will be result left shift operator 1. I'll be going with or here. This one will be bit. So this is kind of formula we'll be going with, result left shift 1 or finally bit, right? So logical right shift n, will be making use of the logical right shift n just to bring the next bit into the LSB or the least significant bit. So this will be n equals n right shift. So this one will be represented by thrice basically 1, right? So n right shift bit 1, right? So this is nothing but the logical right shift n to bring the next bit into the LSB. Next bit we'll be seeing this one. So while we discuss this one, right? The example, don't worry. So now the last step would be after 32 iterations, after 32 this one iterations. After 32 iterations, why 32 iterations? Basically here they have been they have said that we will be going with a 32-bit signed integer for the input, right? So that is the reason we'll be going with the 32 iterations. After 32 iterations, result holds the reversed bit integer. After 32 iterations, results holds the this one reverse bit integer. Result holds what it holds? Reverse bit integer, right? I'll just write reverse bit integer RBI, right? RBI is nothing but the reverse bit integer, right? So this is fine, I believe, right? So this is the approach that we'll be going with. So this is the approach that we'll be going with, right? So now let's implement the same thing on the example one. So see here, let's consider the same thing. We have the 32-bit signed integer here, 432611596, this one 432611596, and the output that we need to get here is 964176192, right? So this is fine, I believe. First we'll start with n equals this one. We'll convert this one to the binary. Here the first step is, so we get this one, right? So this one, this is fine. So we'll start with this one and the binary n equals this one. So for the you can just look into the first 8 iterations, right? So I have showed you the first 8 iterations. So we will be going with the 32 iterations as we had discussed here, right? So here we'll be going with the 32 iterations. I cannot show you all the 32 iterations. I have showed you the first 8 iterations, so you have the idea how the 32 iterations work here, right? So I equals 1, least significant bit is 0 initially, right? So n is shifted. Again I equals to 2, least significant bit is 0, n is shifted. So this one I equals 3, now the least significant bit is 1, right? So here we have 1 at the end, you can clearly see here, right? Now again the least significant bit is 1 here again, so we have double 1, and all we have is 0, so we don't have to this one worry about the initial ones when we go with the least significant bit, right? So this one again, least significant bit is 1 for the 5 this one what do we call, for the 5th iteration as well, after the 4th iteration. So we have triple 1 here, as we have 0, so 1 0 will be lost, and in the place of 0 we'll be having 1, right? So least significant. Next least significant bit LSB is 0 and 0 for the 6th and 7th iteration. So this is fine, man. Finally we have I equals 8, LSB equals 1, nothing but here so we'll be going with a 1, right? So least significant bit is 1, right? See here, this is 1, and at the end it will be 1, right? So this one will be LSB equals 1, result will be this one. So we'll continue until the 32 iterations, right? So the final result would be this one. After at the 32 iteration, result contains this number, right? Nothing but this one, 00 triple 1 0 0 something, ending at the this one followed by 6 zeros, 1 followed by 6 zeros. So when we convert this one into the number, we get the output basically 96. See here, this number 964176192 to the digit, right? So when we convert the binary to the digit basically, so the output that we got here is 964176192, which is equivalent to the output that they have given for the this one they have given in the example 1, or they have provided within the example 1 basically, right? So our approach works absolutely correct. Our approach works absolutely correct. As we are completely familiar with the approach, let's do one thing. Let's quickly discuss the complexities part. So what will be the time complexity and the space complexity here? The time complexity would be big of 1. So why the time complexity here is big of 1? Basically the time complexity would be big of 1 because we are going with exactly this one, 32 simple iterations. We are going with exactly 32 simple iterations, right? So overall time complexity would lead to big of 1, right? So which is of the constant time. This can be written as big of 32 as well, so it's better to go with big of 1. It can be written as big of 32, right? So 32 iterations will be going with, will be performed basically. So what will be the space complexity? The space complexity would lead to big of 1 as well, because we will be making use of only a fixed number of integer variables here, right? So overall space complexity would lead to big of 1 as well. The time complexity and the space complexity for the code that we'll be writing in the future would be big of 1 and big of 1 respectively. Now as we are completely familiar with the approach and the complexities part, we are good to write the code. Let's start writing the code, right? So first step here would be, so we have to go with the accumulator for the reversed bits, right? So we have to start with all the zeros, right? So in simple terms, we need this one, resulting variable to store the result. Basically, I'll just initialize this one result variable with a 0. Next, let's do exactly 32 iterations, man, one per the bit. So let's move on with the iteration part. So this one will be easy. Int I equals 0, 32 iterations. I less than 32, as we are starting with a 0. So this one will be I plus plus. Simple. Now within the for loop, what we'll be doing, will be shifting this one. We'll go with the shift result left by 1 and we'll append n's current least significant bit, nothing but n bitwise and 1, right? So this one I have showed you. So within the approach, so this one will be result left shift 1 or n ampersand 1. We're done with this part. We are only left with one part, so we have to go with the logical right shift n to process the next bit, right? So this one I have showed this one within the approach as well, and right shift 1. We are done with the code. This is it. So finally, what we have to do, we have to this one, what do we call, after 32 steps or after 32 iterations, so result has the bits of n that is reversed, right? So finally we have to return a result variable in simple terms. So let me format the code once and let me hit the run button. Where is run? Run. So this one, yeah, the symbol, I didn't get the run button here. So this is fine. Now the sample test cases are getting passed, so let me hit the submit button, man, quickly. So here you can clearly see the sample test cases are getting passed. I mean, all the test cases are getting passed. So whatever the code that we have written works absolutely correct for all the test cases, right? So yep, I just want to tell you one thing. Yeah, let me tell you when it is required. No need. So this is fine. So I hope the solution part is completely clear along with the approach and the complexities. For now, this is it. Thanks for watching, guys.